Hello students, in previous lecture we have solved some example from exercise 2.6 of R.R. Goldberg. Today we will also continue examples from same exercise. So take the first example. Let Sn is equal to, say, we'll take the odd natural number, product of odd natural numbers in numerator 1, 3, 5 loaded up to 2n minus 1 upon 2, 4, 6 dotted up to 2n for every n. Then show that Sn is convergent sequence. Show that Sn is convergent and 0 less equal limit Sn less equal half. Less equal half. So we have taken the result that every monotone bounded sequence is convergent. Means if given sequence is increasing bounded above, then it is convergent. If it is decreasing bounded below, then it is convergent. So try to show whether it is monotone sequence or not. If it is monotonic decreasing, we will try to show that it is bounded below. And if it is increasing, then we will prove that it is bounded above. Okay. So solution. Here Sn is equal to, what is our Sn? Sn is 1, 3, 5 and so on up to 2n minus 1 upon 2, 4, 6 up to 2n. This is greater than 0 for every n. What is your S1? S1 is just half. For n equal to 1, this 2n minus 1 gives us 1, 2n gives us 2, means Sn is half. What is S2? 1 half into 3 by 4. Means for that half you are multiplying it by 3 by 4. 3 by 4 lies between 0 1, means that resulting product must be less than half, means your S2 is less than half. For S3, again you are multiplying this S2 by 5 by 6 is less than 1, lying between 0 1. If you multiply any number less than 1, the resulting product is less than given number. So by that discussion also you can say that S1 greater than, S2 greater than, S3 and so on. Okay. Now, therefore, what is your Sm plus 1? Sm plus 1 will become 1, 3, 5, so on. 2n minus 1, next odd number is 2n plus 1. Denominator of product of even numbers 2n, next is 2n plus 2. This is precisely Sn into 2n plus 1 upon 2n plus 2. And this must be less than Sn for every n, since 0 less than 2n plus 1 less than upon 2n plus 2 less than 1 for every n. This implies Sn is decreasing sequence, which is also known as non-increasing sequence. Decreasing sequence. So this is 1, this is 2. So from 1 and 2, Sn is from 1 to Sn is monotonic, decreasing and bounded below sequence, and bounded below sequence by 0. And therefore Sn is convergent. Moreover, you can observe 0 is less than Sn is less equal, S1 is equal to half for all n. And therefore your limit of sequence must lie between, therefore 0 less equal limit Sn n tends to infinity must be less equal half. So limit of this sequence lies between 0 and half. In fact, it is 0. Is it clear? Now we'll take next example. Say Sn is equal to, we'll take even numbers in numerator 2, 4 dot dot up to 2n upon 1, 3 dot dot up to 2n minus 1 into 1 upon n square into 1 upon n square. Then show that Sn is convergent sequence. Sn is convergent sequence. So here Sn is equal to, what is it? 2, 4 dot dot up to 2n, product of even numbers in numerator 1, 3 n numbers 2n minus 1 into 1 upon n square. This is greater than 0 for every n. So all Sns are positive. All Sns are positive. Now Sn plus 1 is equal to 2, 4 dot dot up to 2n. Next term is 2n plus 2. Right? Upon 1, 3, so on. 2n minus 1. Next is 2n plus 1 into 1 upon n plus 1 bracket square. Now I cannot write it in Sm form. Okay. Now we'll take Sn minus Sm plus 1. Now Sn minus, or this implies Sm plus 1 is this. Sn minus Sm plus 1 is equal to, if I take difference between the two, so this part and this part, okay, you can observe this part is common in Sn and Sm plus 1. So I'll take it to be outside, 2, 4 up to 2n upon 1, 3 up to 2n minus 1. We'll take this to be outside, in bracket. In Sn it is 1 upon n square minus, from this is nothing but 2 in bracket n plus 1 upon 2n plus 1 into n plus 1 its bracket square. So this 1 n plus 1 will get cancelled. And then this is nothing but positive number. This part is positive. Okay. For this, if I take the cross multiplication now, we'll get 2n plus 1 into n plus 1 minus 2n square upon n square into 2n plus 1 into n plus 1. This denominator is positive. Denominator is positive, which is positive number into, if I take the numerator now, this is 2n square, then 2n plus n, that is 3n plus 1 minus 2n square upon positive number. This 2n square get cancelled. This 3n plus 1 is also positive. Okay. This implies this. Therefore, Sn minus Sm plus 1 is positive, means it is greater than 0, and therefore Sm plus 1 must be less than Sm for every n. And therefore Sn is decreasing, and by this decreasing and bounded below sequence by 1. Bounded below sequence by 1. And therefore we know that every decreasing boundary below sequence is convergent. Sn is convergent. Again, you can observe that its limit must lie between 0 and S1. S1 is 2 here. S1 is 2. Okay. Now take next example. Let Tn is equal to, let Tn is equal to 1 plus 1 upon 1 factorial plus 1 upon 2 factorial plus dot dot 2 1 upon n factorial for all n. So that Tn is convergent and limit n tends to infinity of Tn is greater or equal. Limit n tends to infinity of 1 plus 1 upon n raised to n. Okay. So here Tn is equal to 1 plus 1 upon 1 factorial plus 1 upon 2 factorial plus dot dot of 2 1 upon n factorial. This is greater or equal. T1 is equal to 2 for every n. Moreover, Tn plus 1 is equal to, what will get? 1 plus 1 upon 1 factorial plus 1 upon 2 factorial plus so on up to 1 upon n factorial plus 1 upon n plus 1 factorial, which is nothing but Tn plus 1 upon n plus 1 factorial, and this must be greater than Tn for all n. For all n. Therefore, Tn is increasing sequence. Is non-decreasing or increasing sequence. Now, if I prove that it is bounded above, then we are through. Now, Tn is equal to 1 plus 1 upon 1 factorial plus 1 upon 2 factorial plus dot dot up to 1 upon n factorial. This is less equal 1 plus 1 upon 2 raised to 0 here plus 1 upon 2. What is 1 upon n factorial? This is the next term is 1 upon 3 factorial. Means 1 into 2 into 3. 2 into 3 is greater than 2 into 2, that is 2 square. So its reciprocal 1 upon 2 into 3 must be less than 1 upon 2 square. So 1 upon 2 square and plus dot dot up to 1 upon 2 raised to n minus 1. Is it clear? For every n, which is less equal this 1 plus summation of 1 upon 2 raised to n equal to 0 to infinity. Now these terms are in geometric progression. This is your GP. Okay. This is less equal 1 plus 1 upon 1 minus half. Since summation of r raised to n is equal to 0 to infinity is equal to 1 upon 1 minus r for 0 less than mod r less than 1. So this result we have studied in geometric progression in 11-12 standard. I am just using that one, and it is nothing but half, which is equal to then 3. By simplifying we will get this. Okay, and therefore Tn 2 less equal T1 less equal Tn less equal 3 for all n. Therefore Tn is bounded above sequence. From 1 and 2, Tn is convergent. It is increasing and bounded above. From 1 and 2, Tn is convergent. Okay. Now to show limit of Tn is greater or equal limit of this. To show limit Tn is greater or equal limit n tends to infinity of 1 plus 1 upon n raised to n. So for this, Sn is equal to 1 plus 1 upon n raised to n is nothing but 1 plus nc1, n into 1 upon n plus nc2, n into n minus 1 upon 2 factorial into 1 upon n square, right, plus nc2, n minus 1, n minus 2 and so on upon 3 factorial into 1 upon n cube plus dot dot etc. What will be last term? Ncn. I can write it as n minus 1, n minus 2 and so on up to n minus 1 upon n factorial into 1 upon n raised to n. Again, by taking this is your 1 factorial here. Okay. So this is equal to 1 plus 1 upon 1 factorial, n get cancelled here by taking n square outside, okay, plus n square will get cancelled, 1 minus 1 upon n into 1 upon 2 factorial plus, for this again by taking n outside here, n cube get cancelled, 1 minus 1 upon n, 1 minus 2 by n into 1 upon 3 factorial plus dot dot etc. up to plus, okay. Last term will become 1 minus 1 upon n, 1 minus 2 by n and so on, 1 minus n minus 1 upon n into 1 upon n factorial. Now if we observe these coefficients of 1 upon k factorial, that lies between 0 to 1. Okay, so this is less equal 1 plus 1 upon 1 factorial plus 1 upon 2 factorial plus dot dot up to 1 upon n factorial, which is equal to Tn for all n. For all n. Okay. And therefore, limit Sn is less equal limit of Tn. That is, limit n tends to infinity of 1 plus 1 upon n raised to n is less equal limit of Tn. Okay. So, hereby our part is over. Note, for exact limit of 1 plus 1 upon n raised to n. Take fx is equal to 1 plus 1 upon x raised to x. X belongs to R. If I take this one, okay, or R plus if I take, not taking negative powers, then limit x tends to infinity of 1 plus 1 upon x raised to x. This has form 1 raised to infinity. 1 raised to infinity. If I take y is equal to this, okay, indeterminate form, right? So we'll take here log y is equal to, what is log y? Log y is nothing but x into log of 1 plus 1 upon x, right? And then limit x tends to infinity of log y is equal to limit x tends to infinity of log of 1 plus 1 upon x upon 1 upon x. Now this has form as extending to infinity, this 1 by x goes to 0. 1 by x 0 means 0 by 0 form. So for 0 by 0, what we have to do? we'll take derivative of numerator and derivative of denominator. Derivative of numerator, derivative of denominator. So this is limit x tends to infinity of derivative of log of 1 plus 1 by x is nothing but 1 upon 1 plus x into derivative of 1 by x, that is minus 1 upon x square, upon derivative of denominator minus 1 upon x square. This get cancelled. This get cancelled. So, and then as extending to infinity 1 by x approaches towards 0, so we'll get this to be 1 upon 1 plus 0, which is 1. And therefore, log of limit y is equal to 1. Taking antilog, limit y is nothing but your 1 plus 1 by x raised to x extending to infinity is equal to e raised to 1, that is e. Okay, and therefore limit n tends to infinity of 1 plus 1 upon n raised to n is also e. So in this way we have used L'Hospital rule and corresponding real function to find limit of the sequence. Moreover, Maclaurin series of e raised to x is e raised to x is equal to summation of x raised to n upon n factorial, n is equal to 0 to infinity. Whatever your x in R may be, e raised to x is given by this, and therefore for x is equal to 1, we'll get e is equal to summation n is equal to 0 to infinity 1 upon n factorial, right, which is nothing but limit n tends to infinity of Tn. Is it right? So thus Maclaurin series is useful for evaluating limit of such sequence. Okay. So from this note, limit n tends to infinity of 1 plus 1 upon n raised to n is equal to limit n tends to infinity of 1 plus 1 upon 1 factorial plus 1 upon 2 factorial plus dot 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 2 1 upon n factorial is e. Both are exactly e. We'll take one more example and then we'll stop. Okay. Next example. For c greater than 1, so that, or c greater than 0 in fact, so that limit n tends to infinity of c raised to 1 by n is 0, 1. Case 1, if c is equal to 1, then c raised to 1 by n is 1 for all n, and therefore implies this limit c raised to 1 by n must be 1. Case 2, if c is greater than 1, then c raised to 1 by n is greater than 1 for all n, and therefore c raised to 1 by n must be equal to 1 plus Sn, where Sn is greater than 0 for every n. Therefore, c is equal to 1 plus Sn raised to n. By using the binomial theorem, this is nothing but 1 plus n times Sn plus nc2n into n minus 1 upon 2 factorial plus Sn square and plus dot dot etc. Okay. Now, these terms are positive. Therefore, n times c is greater than n Sn. since other terms are positive in expansion. So we'll get this, and therefore we'll get 0 less equal Sn less than C by n for every n. So if you take limit, therefore 0 is less equal limit n tends to infinity of Sn is less equal limit n tends to infinity of C by n, and which is 0, and therefore by sandwich principle we have limit of Sn is 0, and therefore limit n tends to infinity of C raised to 1 by n, which is nothing but limit 1 plus Sn by using algebra of limits. This is nothing but 1 plus limit of Sn, that is 0, which is 1. Okay, for C greater than 1. Okay. Case 3, if I take 0 less than C less than 1, then 1 by C is greater than 1. 1 by C greater than 1, and therefore limit n tends to infinity of 1 upon C raised to 1 by n is 1 by case 2. By case 2. So what will get? Therefore, limit n tends to infinity of C raised to 1 by n. I can write it as limit n tends to infinity of 1 upon C raised to 1 by n, which is same as limit n tends to infinity of 1 upon 1 by C raised to 1 by n, which is 1 upon 1 is equal to 1. Okay. So thus from case 1 to 3, from case 1, 2 and 3, limit n tends to infinity of C raised to 1 by n is 1 for any C greater than 0. Whatever positive number C may be, limit of C raised to 1 by n is always 0. Okay. So exercise, show that limit n tends to infinity of n raised to 1 by n is 1. This is exercise for you. So with this discussion, today we'll stop our session here. Thanks for listening this session carefully. Stay at home, be healthy, enjoy the online teaching. Bye-bye.